Hey, good day folks, and welcome to the fourth video in my series about terminal games, where we built a game of Snake with Zig. So in the previous video we introduced animation, and for today I want to draw the body of the snake on the screen. So just a reminder of where we stopped last time. If we now run the application and we give the cursor location a direction, the cursor will continue to move in that direction at a given speed, and we can just modify the direction with the keyboard input. Okay, so before we start on the body of the snake, I want to revisit something we did in the second part of this video series. So at the end of our game loop, we've got the surrender section, and what we do here is we first move the cursor to the alt location of the square, and then we paint the board color at that location. Once we're done with that, we move the cursor to the new location of the square, and we paint the color of the cursor at that location. Now, in terms of painting the screen, we've got a number of options. So let's just quickly go through those. Okay, so first, we just always repaint everything. Okay, so what we do here, this would be similar to where we paint out the board. So we'd go to each location on the board and we would just repaint the color what it should be there. Now the problem here is that the terminal is a low bandwidth device. So ideally we wouldn't want to repaint the entire screen at the end of each iteration of the game loop. The terminal would typically be used over like slow network connections or on low spec machines. And even on high spec machines, we're not looking at nearly the same bandwidth we get from copying data between the memory in the RAM and the memory on the GPU. Okay, so what I've done here was a first level of optimization, where effectively I've got two queues. Okay, so we've got a queue for cleaning up artifacts that need to be removed, that should no longer be visible, and then we've got a queue where we paint new artifacts. Now the disadvantage here is that your worst case scenario would be repainting the entire screen twice, because you may have to clean up all the locations on the screen, and then you'll have to repaint all those locations. So what I would want to do instead is I want to have two raster images, and then we paint the diff of those two raster images. Okay, so in this case, the worst case scenario is where we repaint the entire screen. So it's still going to be as bad as the first option. But in most cases, we would only need to repaint a small part of the screen, so we get the same improvement in efficiency that we would have gotten with the best case scenario of the two queues. Okay, so just in case you weren't familiar with the terminology, a raster image is effectively a grid of small colored units. So in the case of, say, Vulkan or OpenGL, the raster would be a grid of pixels, where each pixel would be a screen pixel. But in the context of terminal graphics, we don't really have that fine-grained control over individual pixels, but we can control cells or character locations, where we can modify the colors or whatever symbols displayed at that location. Okay, so let's start by converting our application to use two raster images. So the first raster image, I'll declare where we set up our standard out. So we've got this section over here where we clear the screen and then we paint the board. So after this flush, the screen will be in a known state. So we can declare our screen raster, our first variable over here. So the screen raster will always represent what's currently shown on the screen. and it will be the size of the board, so rows times columns, and the elements will be colored, and we'll initialize that to the color of the board. Now my second raster I'll introduce in the render section of the game loop, and I'll call this the frame raster. So this represents the state that we would want the screen to be in at the end of the render part of the game loop. So again, we initialize it to the board color, and then we will just start filling in the squares that we want to be colored on this frame. So for this I need to do a little bit of arithmetic. So firstly, what we need to remember with both the rows and the columns is that we need to convert from 1 base indexing to 0 base indexing. Okay, so we need to do the same with the columns. Okay, and we'll just set that color to the cursor color for now. Now there's something else we need to do here, some arithmetic. So we need to multiply the row value by the number of columns in the row. Okay, so now we can look at finding the difference between the two rasters. So for this we'll need to iterate over the elements of both raster images. So we've got our frame raster, and because I want to update the screen raster, I'm going to iterate over it as a reference. And then our capture variables will be the source value and our destination value, which will be a pointer. Okay. So first thing we'll need to do is we'll need to check if the destination is the same as the source. So we still need to declare that equals function. I'll just have it as a placeholder for now. So if it's the same, we'll just continue over to the next element. Now, if it's different, what we need to do is we'll need to move to the location for that element that needs to be painted. So let's just quickly work out what the row and the column value will be. So first, the row would be equal to, okay, so we'll need to obviously capture the array index here as well. So so the row will be equal to the index value, and we're going to have to divide by the number of columns. So let's just do a diff trunk. So I and cols. Okay, and then again we need now to convert from 0 base indexing to 1 base indexing. Okay, the next that we'll define or need to find is the column value. So for this we don't need to divide by columns, we just need to find the modulus. Okay, and again we do need to convert from 0 base index to 1 base index. Okay, and then we just set our row and column values to move the cursor. Then let's see what we need to do. Okay, so we'll need to set the color of the source element at that location. We paint it, and then we just update the destination to have the source value. Okay, and then we can get rid of the old instructions over here. Okay, so before we run this, let's go and implement that equal function. Okay, so the first value will be the self value, which is a pointer to a color. And then we've got the other color, and we'll return a Boolean value. And this is just a simple self dot red equals to other dot red, and self dot green equal to other.green and self.blue equal to other.blue. Okay, let's give that a quick go. Okay, so we've got an unused constant. Let's remove that quickly. Okay, let's try that again. Okay, so far it looks good. Okay, we've got a crash. So I'll explain in a moment what happened. Let's go back into our application. Okay, so when we declared our location struct, we used U8 values for the row and the column. Now the reason we picked U8 values was because there's a limited range that the row and column values can be on a terminal. So 255 seemed like quite a lot. Now the problem with this is when we do the arithmetic on our frame raster, so over here we've got a U8 value. So the U8 value gets multiplied by the number of columns, and suddenly we end up with an integer overflow because it's still at this point expect the result to be a U8. Now what we can do here is we could coerce the row value to a U size with something like the as U size, and that should solve the problem. But yeah, I think that's just adding unnecessary code with very little gain. The other option that we can do, let's go back to the definition, is we just can change these to be U size values. Okay, now this means that the location struct is larger than what we need. But in this case, I don't think we're that constrained on memory, so yeah, we can just increase the amount of bytes the struct will keep. Anyway, let's give that another go. Okay, so in this case, it should be able to run to all the boundaries of the square without any crashes. Okay. Okay, so we're finally at a point where we can start working on the body of the snake. So let's go to our game state variables. Now what we need here is we need a variable to keep track of the snake body. So it will need to be a sequence of locations. So let's make that just an array list. And the array list will be of type location. Now the array list needs some memory to back it, so we can either use an allocator to manage that memory, or what I'll do in this case is I'll just allocate some memory on the stack that will be sufficiently large to handle all normal outcomes of the game. So let's call that snake body buffer. Now it will be the size of the board, because the maximum size that the snake can be would be every cell location on the board. And then what we'll need to do is I want to add one more element to it, because the way I intend to use the snake body is I always would start by appending the new head location before I start removing a tail location. Okay, so this is just going to be locations undefined, and let's init it with the buffer. Okay, and we can start by adding the first element of the snake body, which is the location we set earlier. So append and assume capacity, because it knows we've got enough memory, and we just add that starting location. Okay, now instead of calling this location variable lock, let's call it head instead. Because what we'll do is we'll keep on calculating the new location of the head and then add that to the snake body. Now, something else I also want is I want the snake body to grow on every third step. So we need to have a step counter as well. Righto. Okay, so now we can go to where we update the game state. And so we calculate the new location of the head. So once we're done with that location, what we can do here is just append that to the snake body. And then what we can do next is we'll remove the tail if it's not the third step. So let's first increase the step counter. And then if it's not the third step, we'll remove the tail. Okay, it's got a return value that we shouldn't forget. Okay, now the last thing we need to do is we'll just need to update the frame raster. At the moment it's just going to paint the location of the head, so we do need to iterate over all the elements in the snake body and just paint them in. So for this, let's go snake body items, and we'll just say we've got a location over there. And okay, cool. There's going to be some other things we'll need to do, some safeguards, but this is just enough for an initial test run. Okay, so as we can see over there, we've got a snake body that's growing on every third step. Now, things we don't have at this moment is we don't have collision detection. Also, what might happen here is where we hit the edge and the tail keeps shrinking. So we would want to build some mechanisms to handle these sort of situations. And then, yeah. Okay, but for now I think we're in a pretty good situation. So in the next video we can look at handling some of these different conditions. Okay, I'm going to stop the video over here. Thank you for watching. What we'll do in the next video is we'll start implementing some of those game rules in terms of collision detection, both with the snake body and with the edges of the board. Anyway, if you like this video, click on the like button. If you want to see more, subscribe, and I will see you in one of my next videos. See ya.